All right, I'm going to start section 2.3, and it's all about z-scores. And z-scores are related to a standard normal distribution, which we'll talk more about in the next section. Oops, trying to grab my pen here. Always doing this. Anyway, so we have a normal curve, and it looks something like this, and we have 0 in the middle, and some marks along the way, like 1, 2, 3, -1, -2, -3. And these numbers along the bottom kind of tell us how many standard deviations we are away from the mean. And so we can take data points like these here. We'll have x as a data point, x bar is this, the mean of the sample, s is the standard deviation of the sample, and we can use this to kind of place our data point along a scale here. And we use z-scores to compare things that aren't necessarily the same. Now sometimes we have a z-score and we want to know what our data point looks like. This formula here is this formula just rearranged. We multiply by s and then add x bar, and we get this to solve this one for x. A quick bit of algebra. And as we're talking about kind of how this works, outliers are a thing we concern ourselves because they let us know our data set might not reflect what our population is. And so outliers, there are kind of different ways they're established here statistically, but they are more than 2 standard deviations away from the mean. So here if we take x bar and subtract 2 standard deviations, or x bar and add 2 standard deviations, if we're lower than this or above this, this is how our text is going to consider it an outlier, or at least one way. So if I go here, wrong place, and look for a question, I want to jump back a little bit. This one here. It says Sybil's scores 1,352 on the SAT. The distribution of the SAT scores is normal with a mean of 1,024 and a standard deviation of 298. Mayowa takes the ACT score and scores 26. The ACT scores are normally distributed with a mean of 17 and a standard deviation of 5. So we're comparing ACT and SAT scores, which are similar types of things. Maybe their scale's a little different, one more sciencey. There's some arguments on those. But we have kind of apples and oranges, and if we convert to z-scores, we can sort of make them apples to apples. So I'm going to just snip this and show you how I would do this in Excel. Now, it is a pretty good problem here, just like as far as you can add, subtract, multiply, and divide with other ways. But I'm going to use Excel just to sort of track our process here. So for part A, a z-score is what I want to find. And the stuff I have, I've got a data point of 1,352. I have an x bar of 1,024. And a standard deviation of the sample, 298. So then my z-score is going to be equal to, sad face, just kidding. It's coming, 1,352 minus 1,024, close the parentheses, divide by the standard deviation of the sample, and I get this score. Now, that was 1,352 minus 1,024 divided by 298. Can't quite see all of that, but that's going to be okay. Zoom in and out a little bit, might make this stuff disappear. So for the next part, B, and we're supposed to round that to 3 decimal places. We'll get to that in a second. I've got a z-score here. I've got an x, maybe, an x bar, and an s. So we know this is 17. Not sure why this is disappearing. 26 and 5. Does it special for when I'm recording. So my z-score here, going to take 26. Oh, I forgot the equal sign. It's just like, what do you want? Minus 17. Divide that by 5. And again, this is 26 minus 17 divided by 5. So I've got 1.100 and 1.8 as the z-scores, and we have a follow-up question over here maybe. So this was 1.100, 1.8. Assuming both tests measures the same kind of ability, who has the higher score? So this one is higher, something like that. Okay. Now if I jump on over, sometimes we have data points. Here's one where I have a doctor measured serum HDL levels in her patients and found that they were normally distributed with a mean of 60.2, a standard deviation of 3.4. Find the serum HDL levels corresponding to the z-scores. So now we're given z-scores, and we need to work to find those data points. So I'm going to paste this here, see how it goes. X bar, 60.2, S 3.4, and now we're looking to find a z-score that corresponds, excuse me, a data point, sorry, an X is what I have here. I have a z-score. My z is equal to negative 1.6. So, because this is a negative one, our answer should be less than X bar, but I mean a negative value. We're going to be going to the left of the mean there. So, to figure this out, my X is going to be, we take our z-score, oh boy, equals negative 1.6 times our z-score, oh, excuse me, our z-score is negative 1.6, we multiply it by our X bar, 60.2, oh my goodness, we multiply by our standard deviation, the formula, and then add our 60.2. You're not going to believe this. Let's pop over to the notes here and check it out. So X bar plus Z times S. I switched the order here and I talked like a crazy person through it. So here we go. Now, that was going to be X bar, to stick with the formula here, plus negative 1.6 times 3.4. That's what we actually did in a little different order. And we got this. It says to the nearest tenth, so this would be 54.8. And notice that is left of our 60.2. So on letter B here, our z-score is 1.91. So now we're moving to the right-hand side. Our data point should be bigger than our mean. So I take X bar, sticking with the formula, add the z-score, 1.91, times 3.4. And I just typed those all in this time, not really sure why. Sometimes I think it makes it make a bit more sense when you throw the numbers in there versus the cells. Also talking through it a bit, 66.7 is going to be that z-score. So 54.8 and 66.7. Hopefully those really are the values they should be. There it is. All right, I'm going to make another video doing one that's an outlier. It's kind of a sticky problem, can be a little problematic. So